So, good morning, good afternoon, good evening, everyone. Thank you for joining us today for this webinar on advanced tire modeling for better performance. My name is Madhur Olunde, and I am currently working as a FE engineer at VIAS3D. I did my master's and PhD in mechanical engineering from IIT Kanpur, India. Over the past 5 years, I've been deeply involved in the tire simulation, advanced finite element modeling, structure and vibration analysis, and experimental validation. Here, I'm joined today by my colleague, Dr. Akshay Dandekar, Senior FE Engineer at VIAS3D. Akshay holds a bachelor degree from IIT Bombay and completed his PhD from Purdue University. With more than 8 years of experience, he brings deep expertise in solid mechanics, linear and nonlinear simulations, fracture mechanics, material behavior, and physical testing. So we will explore how advanced simulation techniques can provide the powerful insight into the tire performance and significantly reduce the need for the physical testing. In fact, many of the topics which we'll touch today can become a separate webinars. But however, in this session, we have created a comprehensive overview that capture overall with currently shaping the tire industry. So if you're tire experts or you are just starting out, so there is something here for everyone. So let's dive right in. So before going to our main technical topics, just quick look on the big picture. So as of 2024, the global tire market was valued at around $173 billion, and it is expected to grow at a compound annual growth rate of 4.7% in the coming years. But it is not just about the growth, because at the same time, the regulations and norms are becoming more stringent than ever, like UNSC Regulation 117, Euro 7, EPA, or in India, like CMVR. So all these norms with their aim to develop the sustainable products and such as to reduce the carbon emissions or reduce noise, increase the safety and fuel efficiency. And there is another shift that whole automotive industry is now going on, that is shifting from conventional IC engine to EVs. And as we all know the IC engines, so EVs basically don't have or very small noise. So in such a case, tire noise is the most dominant source of the noise. So so it becomes the major area of the concern for both manufacturer and consumer. So as a result of growing, there is a pressure as well as the opportunity in the innovation in tire design and development. So agenda of the today's presentation. First, I will introduce my company VIAS3D. Then I will deep dive into the main our webinar topics, that is tire modeling. So this webinar is divided into the 4 segments. First, I will explain how the tire is constructed and what are the different metal modeling is used. Second part, I will explain the simulation, and in the third part, I will explain how we can automate all this simulation process via 3D Experience platform. Finally, I will discuss on how we can collaborate. Uh, this session will be around 45 minutes. Last 15 minutes we are reserved for the Q&A sessions. So we are the team of 200 plus professionals with consisting more than 40 professionals, with majority having PhDs and masters, with expertise in design, manufacturing, structural analysis, solid mechanics, fluid mechanics, electromagnetics. We are basically the platinum partner of the Dassault Systems globally, and we provide the softwares, resales, and trainings. So we have multiple industry experience such as automotive, aerospace, high tech, oil and gas, petrochemical, industrial equipment, CPG, life science, and manufacturing. So we provide basically consultancy in engineering and PLM, advanced and custom technical support, staff augmentation, 3D experience implementation, training, software, sales, automation, and PE stamping. So here are some example of global industries that VIAS3D has had opportunity to work with and continues to work with today also. This widespread presence reflects the trust that company place in VIAS3D to deliver high quality services across the various sectors. So at VIAS3, we offer a broad spectrum of simulation capability across multiple domains such as FEA, CFD, electromagnet, and AMN. When it comes to tire simulation, our expertise covers everything from basic structural to the advanced, such as the tire interactions or CFD. So basic analysis, such as in basic analysis, we do the footprint, structural, vibration, thermal, in the durability and fatigue under different loading conditions. We do the hyperelastic and viscoelastic material calibrations and tire tire interactions such as the tire water, tire soil, tire snow interaction. The optimization studies using parametric tools and machine learning algorithms. We also deal with the multi-physics simulations such as the coupled thermal mechanical or coupled thermal electrical behaviors. So aerodynamic simulation to reduce the drag and hence improves the your vehicle efficiency. And we also deal with the MBSE that you can integrate your tire with the complete vehicle models. And finally, we do the simulation automation to do the repeatable tasks more efficiently. So in the automation platform, basically I will discuss this in detail at the later stage of our presentation, but this platform allows to manage the entire product life cycle starting from concept and design, moving through the simulation and parameter management, and all the way to the manufacturing integration. So our overall engagement at VIAS3D, our engineering consultancy services are flexible and tailored to client needs, like end-to-end product project supports, onshore, offshore resources, testing, and material calibrations, automation solution using AI and machine learning algorithm, methodology, and workflow process refinement. And as I already mentioned, we are the platinum partner of the Dassault system. We resell the softwares as well as we provide the trainings and advanced supports in various Dassault softwares. So let's start with our main topics, that is the tire. Basically, tire is a complex engineer structure. So here is the cross-sectional view. So if you take the closer view, then you will find the tire actually is a multi-layered structure. So each layer has their own specific functions. And so suppose this is a bead generally made up of steel material. The side wall are flexible for the radial as compared to the bias tires. These are the traits. So basically, it is a complex multi-layer structure. If you take more deep, if you deep dive into the tires, then you'll find this is actually reinforced structure because the rubber is not capable to withstand with the high pressures. So in such a high pressure and different loading conditions like vehicle loads or driving conditions, so these structures are reinforced. So it is, and because of that, it becomes highly anisotropic structure. Similarly, the inflation pressure and driving condition, loading conditions, a tire normally undergoes the large deformation that responsible for the geometric nonlinearity. Rubber are the main constituent of the tire. So the hyperelastic is the main key properties of the rubber. So it is also responsible. So it is also contains the material nonlinearity. Another rubber main property is the viscoelasticity. That is the properties are the function of time. And of course the traits. The traits are the integral part of any tires. So all these designs makes your tire very complex. But when you talk about the simulations, then simulation even becomes more complex because whenever we do the simulation, we have to take care about the tire terrain. So in on which terrain it is we are going to use the tires. So the tire roads interaction becomes the your simulation even more complex. So one by one, the material modeling. So first is the hyperelasticity. So rubber is the, as I mentioned, rubber, the hyperelastic is basic characteristic of rubber. So the hyperelasticity means if you apply the stress and if you release, then material regain its original position. But the stress strain curve during this stretching is highly nonlinear. So if you find, so in such a material, there is not a single modulus of elasticity. So in such a material, the area under this curve, that is the strain energy, is generally used to define the function, and that is known as the strain energy density function. It is a function of strain, but if you define in terms of strain, then it becomes the directional dependent. So to make it direction independent, generally it is represented in invariants. So this I1, I2, I3 are the invariants. So these are the basically parent equation, which is generally used to define any hyperelastic material. And out of that parent equation, there are various scientists which they have generated or developed their own equations, like here Newhickian, Munirevlian, Ogden's, or Morlow's. So in the Abaqus, such a hyperelastic modeling is very convenient. So Abaqus gives the wide range of already existing model, or you can, if there is a new model which is available in the recent literature, so you can model that also using the subroutine function. So there are Abaqus gives options, like if you are already curve fitted data where you have already generated the constants, then uh, you can just uh, add that constants, or you can use the directly test data. So Abaqus allow you to give unixel or biaxial or volumetric test data. So generally such a test data is generally used measured using the DMA or UTM machine. So here VIAS can help in the material testing and calibration program development. Next property of the tire is the reinforcement. So there are two options basically when you define the reinforcement. First is the mechanics. You can use the mechanics of the composite material, and second option. So here you can develop the, you can find the equivalent property based on its constituent. Like here, these are the fiber properties and these are the matrix, and based on that you calculate the equivalent properties for the given composite lamina, and you can put that property in the orthotropic material, or you can assume it is a fully anisotropic. And the Abaqus metal modeling definition, you can assign directly this property to the lamina by assuming orthotropic or anisotropic. But there is another approach, that is direct approach. In the Abaqus, there is Abaqus gives the rebar modelings. So here you can directly put, instead of calculating the properties, you just put the area per cross section of the rebars and spacing between the rebars. Based on that, Abaqus calculate the equivalent thickness. And in such a modelings, Abaqus basically treat two separate elements. Like the matrix material, it will act as a host, and for the inside the reinforced element, it will treat the separate two-dimensional element like shell, membrane, or surface. So if you go to the section and if you define the shell homogeneous, at the bottom you will find this options. This is basically the for the definition of the rebars. So you can mention the area per rebar, spacings, or if there is a different orientation angles in the fibers, or even positions. So another important characteristics is the viscoelasticity. Basically, viscoelasticity is the your material property are the function of time. In the viscoelastic, basically two tests are very common, that is relaxation test and creep test. In the relaxation test, we apply the constant strain and we keep the sample for the fixed strain, and we check how the stresses are varying. Then we observe the stresses are basically decreasing over the time. So it is so in such a case your modulus is the function of time, that is known as the relaxation modulus. In other way, in creep test we apply the constant stress and we keep the sample for the constant stress, and we observe over the time. Then you feel the length of the sample is increasing for a given stress. So it is a basically creep test. So here we measure the creep compliance. So if you want to define such a material in the mechanical models, so there are two types of the models available, or generally viscoelastic material defined to basic building blocks, we can say, are these the Maxwell and Kelvin. In the Maxwell, the elastic and viscoelastic part, these are arranged in the series, while in the Kelvin these are arranged in the parallel. So these are the equation of your modulus of elasticity and compliance. But in actual material, generally such a but actual material will have the Maxwell or Kelvin model in the series. That means this tau, that is relaxation time or relaxation constant, basically have the multiple relaxation constant. So in such a case, we generally represent the material in terms of combining these building or these basic blocks in parallel or in series. So here is the equation. Such equation generally termed as a Prony series. So if you want to, now there is another approach. Suppose if someone is interested how the viscoelastic material behave in the dynamic loading, then in such a case the dynamic strain, that is the strain which is a sinusoidal or fluctuating strain, is applied. So such a case, generally we will get the complex modulus, which is function of frequency. Here real part represent the storage, and and imaginary part represent the your uh, or loss part of your viscoelastic, and the relative relation between this real and imaginary basically represented in the tan delta. Basically it gives the damping coefficient of the given viscoelastic material. Such a viscoelastic material property are generally defined using the DMA machines, or there are DMA machines which can also incorporate the temperature effects along with this dynamic. In Abaqus, such a viscoelastic material can easily defined. Abaqus gives allow you to both, whether you can put direct test data, that is the clip test data, relaxation test data, or if you have the this constant which you already developed, like Prony series, so you can put that. So also it allows to put the data in the time domain also. So these are the main material property. So now let's start with our tire simulations. So first is the static analysis. The static analysis is a very we can say it is the fundamental analysis in the tire in any tire design. So where generally we only use the cross section of the tires, or generally half cross section. We apply the boundary conditions like remounting, and as well as the loading conditions such as inflation pressure. Now we solve these problems, we find the stress and strain, and this stress and can be directly transferred to the three-dimensional problem using the Abaqus inbuilt function like symmetric result transfer. So, and then once full model is ready, then we can do the further analysis such as the contact with the ground surface or vehicle load at the axle. So this approach is very computationally efficient, because if you apply the inflation pressure on full three-dimensional, and instead of compared to that problems, if you follow this axisymmetric or symmetric result transfer approach, this is almost 60% faster than conventional. So why the static analysis so important is the footprint analysis. So footprint analysis is one of the most important and fundamental steps in any tire simulation, because it is the starting point of many advanced simulation like steady state rolling, brake force evaluation, and tire road interactions. Like in contact patch behavior, you will get how your patch is or contact, how the pressure is distributing, or is there any stress concentration is happening when tire is under static loading. Similarly, performance optimization, because the contact patch is generally gives the how the friction is happening between the road and tire. So it is also responsible for the fuel efficiency, so you can optimize for the better fuel efficiency. And again, the safety and durability also, the contact patch has the very important role in the safety and durability, such as the different driving condition, full tractions or braking and cornering. So your vehicle, how your vehicle perform is largely controlled by how your contact patch is static. So next stage or next simulation is the steady state rolling analysis. Basically, in the steady state and rolling analysis, using the steady state transport option, which is inbuilt available in the Abaqus, one can use the footprint analysis result in static case to model the steady state dynamic interaction between rolling tire and rigid surface. A steady state transport analysis uses a moving reference frame in which rigid body rotation is described in Eulerian manner, and the deformation is described in the Lagrangian manner. This kinematic description converts the steady state moving contact problem into purely spatial dependent. So in such a case, you need only the fine meshing at the only where your tire is coming to the contact with the road surface. So what is the importance? So what is the, just briefly to understand what is the Lagrangian and Eulerian. So in the Lagrangian approach, when you actually your mesh also deform with the materials, but in the Eulerian case, your mesh remains undeformed and material actually flows through that mesh. So what are the important? So importance in the steady state rolling analysis, because it helps to evaluate the tire behavior under real driving conditions like slip, braking, and cornering, which are difficult to replicate in the static analysis. So these like a slip angles, this is very important in the cornering, and to understand how this slip angle is deforming in actual rolling conditions, so that can be understood this tire simulation, that is rolling analysis. Third part is the transient analysis. So in the during the actual driving conditions, tire often encounter sudden obstacle like road, breakers, curbs, slit, rough patches. Understanding how a tire behaves in this dynamic situation is absolutely critical. This kind of short duration, high impact wear is the best captured to the transient tire analysis in Abaqus. Typically, such an analysis is performed using the Abaqus explicit analysis. But the one of the important challenges when you do the Abaqus explicit, so time step is very important. So we have to keep the time step very small. So in such a time step, if you do the complete analysis like rollings and transient analysis, then it will be very computationally costly. So in such a analysis, generally two steps are performed, in which the rolling steady state rolling analysis is used, the previous which I explained Abaqus standard, that is implicit method, and in the second step we use the Abaqus explicit, and the result from the steady state we can directly transfer to the explicit analysis. So this coupled approach is very cost effective. Oh yeah, the another important analysis in the tire simulation is the vibration analysis. So what is important? Because the structural stability, because we often heard that during the driving, actual tire just get burst out suddenly. So this is due to the main, either it's the temperature reaches to the extreme level, or it's a vibration is increased to the critical level. So so keep the vibration below particle level is very important for the structural stability. So also there are two important aspects like in cabin vibrations and tire road interaction noise. So these are the main important aspects which considered during the tire vibration analysis. So in the Abaqus, there are basically two analyses are performed. First is the free vibration, where the modal analysis like how your tire is tire's natural frequency and corresponding mode shape. So here this governing equation is used, that is equation of motion. And in the second we use the forced vibration, or generally we use known as the steady state dynamic analysis, where the FRF equation is FRF plots developed, and from that which of the key frequency are resonant are find out in such analysis. So the Abaqus gives three different approach: direct solution, subsequent method, mode based method. So these each method has their own advantages as well as the demerits. So it depends upon the which method is suitable for the given application. So as I mentioned, the FRF is basically used for to characterize the vibration performance in of the tire, but it is actually helpful under the low frequency vibration, because if you increase the frequencies at higher frequency, your eigenvalues are densely populated, and your eigen mode shapes and mode shape of the tire become very complex. So in such analysis, generally the FRF is not useful tool. So there should be the another approach, and here is the so such analysis generally termed as a waveguide finite element method. So in that, basically you assume that that the waves are actually traveling along the circumferential direction of the tire, so in which you need only the cross sectional meshing data, and other direction you use the analytic formulation. So sometimes this method is called as a SAFE, that is semi analytical finite element method. Other factors like all the material and structural properties, you can the same similar to the three-dimensional model, you can add in the main tire. And when you but in this in such a case, your equation of motion will become the twin eigenvalues problem. So in earlier it was only the omega, which is natural frequency, was the unknown, and but in this there are two eigenvalues like zeta and omega. Here zeta represent the wave number, that is how your tire vibrate over the space. So if you do the simulation, then you will find the mode shapes and natural frequencies. And if you do find the steady state vibrations, So you can calculate the steady state vibration or puff or response of the tire for the given ground excitation. So here the straight line basically represent the waveguide result, while dotted line represent uh, the the 3D FEA simulations. So if you see, these are the very but the computationally waveguide finite element is very cost effective. And yeah, so there are another aspect of this waveguide approach, because instead of analyzing the each eigen values, so you can analyze in the group of eigenvalues, and that group of eigenvalues generally represent the wave characteristics, the which travels along the tires. So when tire vibrates, which waves are basically traveling, which waves are damping out due to the viscoelastic damping. So you can analyze through such a curves, and this curve is nothing but the wave number versus frequency, and generally represented as the dispersion curves. So after the vibrations, there are another approach, simulation, one of the important simulation in the tire domain, that is the coupled acoustic structure analysis. Generally generally in automotive, so there is a vibration observed at in cabin around 200 to 250. So if you do the simulation of the tire only, and if you do the FRF, generally it is not showing any vibrations coming from the uh, coming through the tire. So but when you solve such a when you solve tire with the air, so in such a couple analysis, there is an additional peak. So basically, this is called as a air cavity resonance. So if you do the only simulation with the tires, so you will not see this peak. But when you solve the coupled problems, so there is additional peaks. So such a are very important in the vehicle interior noise. And Abaqus has the very good uh, 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 capability to solve such a problems using the adaptive mesh. So here basically the dynamic analysis, first at dynamic analysis of stationary tire is carried out in the first step. In the second step, the tire air coupled analysis, and in the third step, the air is at rest while the tire is in motion. So by doing this three-step analysis, one can easily identify so which peaks are basically due to the this coupled response or coupled reactions. So this is again one of the important analysis which is generally the tire industry perform. The VIA analysis, again one of the importance, because to define the life of the tire, so VIA analysis is very much important in tire industry. So in the tire simulation, basically three initial steps are very similar to steady state or rolling analysis. Like you take the axisymmetric model, inflate, and do the simulations, stress and result transfer to the full three-dimensional model. And once the full three-dimensional model you develop, then this three-dimensional model you can calculate in steady state rolling analysis, like stress, slip rate, and the fractional energy. So by using that like slip rate and fraction energy, so you can use that outputs or results in your VR model, such as the Archer's law. So this is basically used to define how the tire is wearing out. And then using the U-mesh motion subroutines, you can define the ablation velocity at each tread surface node. Basically, ablation velocity is a virtual velocity vector applied at the surface node to mimic the removal of material over the time based on the wear model. So in such a case, the adaptive meshing is very much important, because using the adaptive mesh, so you can directly identify how your tire is wearing out over the times. When you do some simulation, let's say tire is running around 10,000 kilometer or 20,000 kilometer. And also this simulation also at the end, you can also check how your the footprint analysis is changing over the time because of this in the worn out condition. So such analysis is very conveniently handled in the Abaqus environment. So again, one of the important and little complex simulation, that is tire interaction analysis. In such analysis, basically there are different categories like hydroplanings, where you analyze the tire with the water, and in second, tire gravel, tire soil, and tire snow interaction. So all these simulation, there is a common approach like coupled Ehlerian-Lagrange approach, where the you use the Lagrangian approach where the your material and mesh both deforms. This approach you use for the solid elements, while for the fluid elements you use the Ehlerian mesh or Ehlerian approach, where your mesh is remains constant, and using the law of conservation of momentum, so you calculate how your material is flowing. So in the tire level interaction, there is a slight difference, because here generally the discrete uh, element method is very suitable for such analysis, where you can model each gravel as a rigid surface or deformable body. But this is very computationally expensive, because such analysis is performed in the explicit Abaqus explicit. It gives the accurate result, but it is computationally very expensive. So instead of doing this, you can assume in the bulk, and like crushable foam, and here you can model such a in bulk using same coupled Ehlerian-Lagrangian approach. Similarly, tire soil interaction or tire snow interaction follow the same approach, where you can use the advantage of both Lagrangian and Ehlerian formulation. So another important is the tire simulation trade optimization. So basically, again, the trade optimization is very important, because there are different sources of the noise. Basic tires, there are different sources of the noise. So like a trade element impact, running deflection, road texture impact, and also there are some CFD phenomena like air turbulence, air displacement, sticks, snag adhesion. And in first two row represent the sources of the noise, while bottom represent the resonance, the noise get amplified. So in such a case, so it is important to analyze, so out of that, the trade impact is one of the primary source of the tire noise, because it is responsible for the tire vibration, and the tire vibration is generally further responsible for the acoustic or pressure fluctuation, that is the noise. So uh, impact noise is basically caused by the trade patterns. So as most of you know, when the tire rolls over the road, the trade blocks repeatedly hit and leaves the road surface, generating impact forces. These forces excite the local vibrations. That's one of the main reason we hear the tire noise. So now this type of the simulations is now is gaining very popularity in the recent research, where the different industries focusing how we can optimize the tire trade patterns, so that they can minimize the overall vibration due to the impact. So here the approach is you just and in tire, basically, that there are different patches, different pitch, like different uh, trades are used. So the reason behind, because if you use the single trade, then there will be the noise, concentrated noise. To avoid that, generally tire has the different patch, and it is randomly oriented. So the approach is first model the tire noise prediction model. So in this, sound pressure linked to with the vibrations, such as we can say FRF. So you develop the FRF or transfer functions. Then instead of redesigning each time the new trade patterns or new shape of the trade patterns, just develop some basic shapes, like that is called as the basis vector method. So here base 1, base 2, base 3, base 4, and like g represent the base vectors. So here you change some modification in the tire trade patterns, and then you can, by using this equation, you can develop the, by the combination and the using the weight functions, you can develop the uh, new trade patch. And for that, now use the optimization algorithm to minimize the your vibrations, like excitation force, as well as the output, like your response or nodal displacement. So for such a optimization, generally the genetic algorithms are very commonly used. So when such a simulation is performed, so one can see the original tire geometry versus the optimized. So here, if you see, there is a slight change in the lateral group patterns in the left region, in the right region. So this is the optimized tread patterns, which is responsible some maybe 5 to 10 dB noise reduction. So such a type of the simulations are now gaining very popularity in the tire industries. Now our third section of today's presentation, that is how we can automate the entire lives or entire simulation, tire simulation, using the 3D expense. So what is the basically 3D expense? The 3D expense is basically, it is a platform which integrate design, simulation, testing, and life cycle management. So it is connect the entire ecosystem of your organization, and it is a digital platform. It is a cloud-based platform. For example, in tire, if you want to do the complete tire, like from very starting from your ideas to the complete manufacturing and it's a testing. So you can start with the new designs where we can use the Dassault, CATIA, and SolidWorks. So, and once your model is ready, then you can perform the simulations using the Abaqus, and where you can do the various simulation which we discussed earlier. Then you can use the PLM integration. So here you can check which version you are, so you can control the version traceability and collaboration with the entire teams like design and simulation on manufacturing teams. Similarly, you can use the Delmia software for the manufacturing and process planning. So here like in the manufacturing, so you can in on this cloud platform, you can also monitor the how the validate your mold geometry, simulate the extrusion or curing, and even optimize the product layout before anything goes to the shop floor. Finally, once your tire is ready, then you can also use the for the data analytics, such as the test results, simulation output, and field data. You can visualize, compare, and fed into the machine learning algorithms, so to predictive modeling and optimizations. So this is the cloud-based platform where you can single platform, you can monitor entire product development cycle. So it is very time efficient and cost effective. Faster design iteration and democratization for the designers are the key characteristics of this 3D experience platform. So for example, optimization and the automation are the important factors come along with the 3D experience. For example, if you want to optimize, let's say DOE, to minimize the contact pressure between the rim and tire. So in that, you define the models, you apply you just mount on the rim, and you just develop one DOE, and you set some output parameters versus input parameter, and you plot, and you can optimize. You can see how these input parameters are basically is relating with the output parameters, and you can optimize this parameter. So such a templates you can easily develop in the 3D experience platform. Similarly, you can develop the template for the automations in the 3D explain platform. Like in conventional software, conventional methodology, generally when we do, let's say, footprint analysis, so we do the axisymmetric, then apply pressure, then axisymmetric result transfers, and the full 3D tires, and then tire with the road surface, and we check how the footprint results are coming. So if there is some modification, then we go to the back, and again we have to do the same process again. But in this automation, if you do some modifications, all the other steps will automatically adjusted, so no need to do the further process. So this is such a type of the automation is very easily handled in the 3D expense platform. So our last discussions, so how we can collaborate. So working with VIAS3D, so we can give the complete training. So there are 2 sessions. First is the fundamental. So this is the 2-day session. We can give the comprehensive basic analysis like footprint, how we can model the reinforcement, different approach of the reinforcement modeling that I explained, like contact modelings and different materials and accessibility. There is another training session where we can use the detailed training about advanced topics such as steady state rolling using the Illyrian techniques, or hydroplaning, tire interactions, or how we can do the structuring and submodelings, and even transient analysis using Abaqus explicit. Work with VIAS in consultancy. VIAS has, as I mentioned, has capability to do complete tire analysis from the hydroplaning, force, movement, footprint, and aerodynamics, drag, noise, and vibrations. Here, VIAS can provide help to the project basis consultancy, or whether it is short duration or for the long time relation. So again, if you are already tire industry or tire persons, uh, so VIAS can help you to automate your entire product life cycles with the full automation. So during this development, there are a lot of templates makings required, like where the scriptings are necessary, and so in such a entire automation, that VIAS can help you to automate the complete simulation process from starting to manufacturing. So last, so VIAS3D value. So we are prompt and complete technical solutions we provide. We have the expertise in the different industries, application and software solution. So we reach technical consultants, experience, and software agnostic. We transport the knowledge through the training and services. We are very strict in the quality controls, and we are flexible for in pricing for the startups. And VIAS is a one-stop solution where you can do the multi physics simulation like CAD, FEA, CFD, EMAG, GUI, root cause, and optimizations. And we provide the global resources and onshore and offshore. Thank you. If you have questions, I'm welcome. Thank you, Manuel. Thank you all.
All right. Thank you so much for that great presentation. We're going to give it a couple of minutes to see if we have any questions in the Q&A section. Feel free to drop any question that you may have, and we will be addressing them shortly. Right, so we have Sumit has a question. Can you please drop your question here in this chat? All right. In the meantime, we also have another question right here, which is, what are the differences between direct versus subspace versus mode-based method in Abaqus? And which method should be used in this case?
Okay. So basically, there are three different approaches in the Abaqus: the direct, and subspace based, and model based. So in the direct, basically, if you know the equation like k minus omega square m, so this equation of motion, so here we find the eigenvalues and eigenvector by direct taking the inversion of the whole stiffness matrix. So this is called as a direct approach, but it is accurate but computationally efficient, because we have to take the inversion of whole mass matrix, and it is really expensive if you have large degree of freedoms. Another approach is the subspace based method, so in which basically we reduce the dimensions by using the eigenvectors. And in such a case, generally again we calculate the new mass matrix stiffness, or if there is a damping, and again we find the eigen values and eigenvectors. So there are third approach where we do not basically we use directly eigenvectors to calculate the response, where the eigenvectors mass normalized eigenvectors are, and its orthogonality property are used. So it depends upon your applications or requirements, like if you are so if you are worried about the accuracy, then you should go for the direct methods, because it is more accurate. But if you are if you are fine with the reasonable accuracy, but you are worried about the efficiency, it should be fast, then should go for the model based method. Hope I answered your question.
All right, thank you so much. We have another question right here. Nowadays, we can see random tire threads in high-performance motorcycles. Can we use the symmetric modeling for such case?
Okay, can you just repeat once again?
Sorry. Nowadays, we can see random tire threads in high-performance motorcycles. Can we use the symmetric modeling for such case?
Yeah, we can use axisymmetric modelings in such a case. Basically when we do the axisymmetric modeling, so we are basically interested in the footprint analysis. And when such a analysis basically because random trade patterns are there in tires, and if you want to analyze the effect of the trade patterns, then there is important to do the complete three-dimensional problems. But if you do such analysis where the trade patterns do not have large effects, so axisymmetric modeling is very convenient. Yeah.
All right, thank you so much. We have another question here. How do you ensure that the transition of results between Abaqus standard and Abaqus explicit does not introduce numerical inconsistencies or affect accuracy?
Okay, so in the Abaqus, the transition between the standard and explicit is handled through the well-defined the restart file mechanism. Basically, there is a restart approach, because you directly do not switch from the standard to the explicit. So there are the restart approach where the steady-state rolling analysis in the Abaqus standard, and the results like stress, strain, displacement is saved and first is mapped onto the model, and this becomes the initial condition to your the explicit steps. So generally we use the nodal based mapping rather than the global interpolation. So this ensures that the stress fields and the kinematic states are very correct at the nodal. And the other factors like mesh compatibility, so we ensure that the mesh in both Abaqus standards and explicits are same. So this in between step, that is the restart file mechanism, ensures that there should not be any inconsistency or model convergence issues. So this can be effectively handled in the Abaqus.
All right, thank you so much. Seems like we don't have more questions. In that case, again, thank you everyone for joining. Thank you, Madhav. We hope that you find this session insightful and helpful. And if you have any question or any feedback, we'll be more than glad to receive that information from you guys. And I don't know if you would like to say something else before we finish.
No, thank you all.
All right. So
Yeah,
thank you
we
so
can
much
finish.
and have a great day. Thank you.
Thank you all.